Okay. Last class we discussed about regression. Hmm? So how we got motivated from regression is like if we have real data sets, if we have some real data sets, so if we have some real data sets, then for example, I gave you an experiment to do that if we have a wire, like we are considering this experiment, suppose, okay, if we have a wire and we pass voltage through it, it is under our control, and the current flows through it. It depends on the resistance and the voltage supplied. Okay, so current is not in our control, but voltage is in our control. How much voltage we give? So voltage and current. Okay, it's the only data we have with us. Okay, so the idea is how to compute resistance. Okay. So what we did, we constructed a lot of experiments around 10-50 times we have to measure. Okay. And at every time you will see the resistance will somehow change. It won't be constant. Okay. So, but if you already know the formula for Ohm's law and all, it is V equals to IR. You already know from physics from your school days. So what to do? The idea is like, can we construct the data points in VI plane? Okay. And then you will see that the points are all scattered. The points are all scattered. Okay. The points are all scattered. So if the points are all scattered, uh, we try to understand how we can have a formula for it, or how we can approximate, or how we can estimate. Okay. So regression is nothing but an estimation. How it's not about finding the best, I mean, the perfect line for it, okay, or the curve for the formula, but it is the curve which can best estimate the data you have. So as I told you last time, I plotted numerous curves that can serve as a regression line. Okay, you can see green, blue, red, cyan curves on this figure, which can serve as different regression lines. But then it means that regression line is not unique. It is not unique because you can have, based on a particular data set, you can have multiple set of regression lines. Okay. And regression line is not unique, but this causes a lot of trouble to the scientist. I mean, if regression line is not unique, then how are you going to fit? Okay, how are you going to fit? So what the best method? So we need to find a best method. The best method was, can we find a regression line? Can we find a regression line which can best fit the data? Which can best fit the data means which can be a best estimator for your data set. Okay, that means the error of the residuals has to be least. What is the residual? It is the difference between the obtained data point from your data set and the given regression line. Okay, and you take today we will see, why don't you take the sum of errors? I mean, why don't you take the sum of errors? Take the error here, take the error there, error of all data points, and add it up. That should be the error. But actually, that's not the case. What we actually do is we take the square of the residual and we sum them up. So therefore, it is known as, and we try to minimize it. So therefore, least is coming because you are minimizing and you are squaring that residual term. Okay. So it is least squared and error. Okay. So therefore, least square regression. Okay. This is the motivation of why the name is called least square regression. I hope you got the idea. Okay. But we will see first that why summation of EI doesn't work, but summation of EI square, residual square, will work. That we will see, we will obtain. And keep in mind that regression is a kind of supervised machine learning. Okay. So I suggest that in your machine learning course, whatever you are learning, try to make a connection to this. I mean, why regression is referred to as a supervised machine learning technique. Okay. And why it can't be unsupervised. Okay, fine. But before I move, so there are error in our experiments. There are error in our experiments. Okay. However, we cannot get those errors. We cannot find those errors because those errors are made due to humidity, those errors are made due to temperature, those errors are made due to air pollution, those errors are made due to the humidity content of the surroundings. Those so many parameters are very difficult to control. So we cannot determine this noise. Even if you determine one noise, there will be some noise which you cannot determine. Okay. So therefore, noise will be there, but you cannot determine it. But we know it that it is there. So therefore, um, you can see we don't get a perfect regression line. And let us come to an analysis why you can't evaluate this noise. Okay, why you can't evaluate this noise? Okay, so hmm, let me see. Okay, so noise are due to many sources. Okay, and here you can see I have listed down this condition. Okay, I equals to Vi by R. Okay, it's not following I equals to Vi by R. It is not following that. Okay, it is not following that. Therefore, why it is not following that? Because some error is there. So that error is nothing but epsilon I that we tried to model it ourselves. I mean, we wanted to catch the error to tell that there is an error epsilon I, and that epsilon I is sum of all errors. I mean, humidity error, temperature error, okay, rust error, any air pollution error, whatever. So, but we cannot eliminate this noise. Okay, we cannot eliminate this noise. Okay. Now let us see it from a linear algebra perspective. Okay, I hope a lot of you already have linear algebra in their bachelors, right? Number of equations, number of unknowns, you have it. Now can we think this equation written over here marked in green from that perspective? Okay, so from that perspective, right? So how can we do this? Hmm? How can we do this? Let us see. But there is a speciality about this error. Okay, there is a speciality about this error. What is the speciality about this error? Okay, the speciality about this error is like it has zero mean. Okay, it has zero mean. Let me write this epsilon I. That means zero mean means epsilon I. This is zero. Zero mean. Okay, zero mean, and it is a random noise. And it is a random noise. Okay, random noise. What does it mean? Random noise. It is independent. It is independent of V. It is independent of the voltage. Okay, I mean it is there. It is not like you put some 10 volts voltage and therefore it came the noise. It was already there before and after applying the voltage also. Okay, good. Now how many equations are there? That's what I want to ask you. Considering this green curve, how many equations are there? So that depends on I and Vi. That many number of equations will be there depending on I. So how many data sets we will have? So we can say I is equal to 1, I is equal to 2, like that. I is equal to n. We can have n data sets. That means we can have a pair of Vi. Okay, we will have a pair of say I and Vi, and I equal to 1 to n. So these are your data sets. This is the set of experiments you carried out. These are the sets of experiments you carried out. Okay. So therefore, how many equations will be there? N equations. Yes. So there will be n equations. But now I am asking you, how many unknowns will be there? How many unknowns will be there? Hmm? Think carefully. How many unknowns? It's you are neglecting something. You are forgetting why are we doing this experiment for? Hmm? Which one? Pair them. Yeah, what she told is almost correct. What she told also is almost correct. But they need to talk to each other and come to a conclusion. Huh? Which one? Hmm? Yes. n plus 1. Why? 1 4? Yes, exactly. So there are how many unknowns? So epsilon 1, epsilon 2, like that till epsilon n. But don't forget that r is also an unknown. R is also an unknown which we are trying to find using regression. R. So this tells us that there are n plus 1 unknowns. Now tell me, there are n equations and n plus 1 unknowns. So my question to you is, what can we do with that? What can we do? I mean, can there be a unique solution? There are n equations and n plus 1 unknowns. Can there be a unique solution? Think from a common sense perspective. Don't try to remember your formulas, whether n greater than this is no equation, all solution, infinitely many solution. That things don't remember. But think like this, n equations are there. So n variables can be controlled. Right? Each equation I can control with some variable. N variables are controlled. Remaining is one variable that can move around freely. That can move around freely, right? And if it can move around freely, there can be many solutions. It is free. There is no equation to bound it. So it is free. So therefore, this nature of solution has no unique solution. I mean, there can be any solution you like. There has no unique solution. Okay. Now let us do second case. Okay, let us do the second case. Let us do the second case, case 2. So you saw that if we are considering noise, then it becomes not a unique problem. I mean, we are doing a problem which has infinitely many solutions, no unique solutions. Okay. Okay. Now you tell that, okay, the problem is due to noise. The problem is mainly due to noise. Let us neglect the noise. Let's neglect the noise. Okay. Neglecting the noise means epsilon I equal to 0. We are setting epsilon I to be 0. In that case, okay, can you tell me? Then it will be II equal to Vi by R, right? II equal to Vi by R. Okay. So how many equations are there? N equations. How many unknowns are there? Hmm? Yes, one unknown. That is just R. Okay. Now you tell what can be done. So number of equations is greater than number of unknowns. So what should we get? Hmm? Yeah. Hmm? Hmm? Unique solution? No solution. No solution. Why? Because one equation will tell that this is R, another equation will tell that that is R, third equation will tell you that is R. From every equation you are solving R. So, I mean, you cannot have a single value of R. You need to find a single value of R which satisfies all of them, right? So here, no solution. No solution. Okay. And this is n is very bigger than one actually. N is the number of data set you usually consider, and always the data set is very big. So therefore, instead of n greater than 1, I have written greater than greater than. I mean, n can be something like 500. So 500 just greater than 1 is not that interesting. 500 is actually greater than 1. Okay. So n greater than 1 is actually a over-determined system. I mean, you are over-determining it. You are over-determining it. Okay. You got the idea? You are over-determining the system. Okay. I mean, you are giving the R value much than it needs. If it was just one equation, you can simply find out, right? So therefore, you cannot find a unique R and all noises exactly. From both these cases, we came to know that you cannot find all epsilon i's, all noises, and R simultaneously. You cannot find. That's what these two told you. Okay. Now, instead of telling you this logic, if I had told you you cannot find noise, you cannot find resistance, you might not believe me. But through this perspective, linear algebra perspective, when you think, it comes out to be exact. It depends on the number of equations and number of unknowns. And you can easily see why we cannot do it. Okay. Okay. This you understood, no? I mean, you can get something like R is equal to 1 R is equal to V1 by I1. Another R you will get as V2 by I2. Another value of R you will get as V3 by I3. There is not a single value of R. And what you are telling that there is a single R which satisfies all of this. It is not possible, overdetermined. So therefore, it will not have a unique solution. It won't have a solution. Okay. So therefore, what we are doing is, our aim is here to estimate. Our job is not to find the R. Our job is to estimate the R. Our job is to estimate, not find the exact value of R, but to estimate it. Okay. So therefore, you can see that we are always talking about minimize the residual, not to tell that find a line which can fit the data exactly 100%, to estimate. So to estimate R, okay. And so this is like known as this technique. This technique is known as parameter estimation. Parameter estimation. Okay. And one such best technique you can know is the least square method. Okay. Huh. Okay. So it's a least square method. Okay. Fine. I think we already discussed much of it. Okay. Okay. We discussed about the cost function and the loss function, right? So loss function is actually for per data point. Okay. The loss function we discussed last class, that is EI. You know what is EI now, right? So these are the data points. So EI is nothing but the difference between the data point and the regression line. So this is the EI. This is another EI. This is the difference between them. This is the another EI. This is another EI, right? For each data point, you will have a EA, right? So that is known as the loss function. So loss function, actually, we are considering per data point. Per data point. Okay. However, cost function is nothing but the overall error. I'm just going through the previous class a bit so that we'll be on the same page. Okay. So what we understood, consider a discrete data set. Okay, consider a discrete data set. And the idea is, suppose the data set, training data set looks like this, xi, yi, and I equal to 1 to n. So there are n set of data points. And then if what we do is, given a value of x star, we want to find the value of y. We want to estimate the value of y at that point x star. Okay. So that is means that we want to find y star such that y, it is y of x star. Okay. I mean, given a value of x star, given all data points, okay, then we will say that, okay, I will give you this x star value. Can you estimate the y? That x star will not be in the data set. That x star won't be in the data set. So is it clear, or shall we do it again? It's clear. Okay. So what we do is, if, I mean, later we will see that there is no reason why to take this regression line in the starting point. There is no reason. Okay. So because the data is spread like linearly, therefore we think that we can fit a linear regression line, a straight line. Okay. This is the motivation that we can approximate the regression line by W0 plus W1x. However, later in Python, we will see that if your data sets are spread like, something like this, If it is like this, can you take the regression line as a straight line? No, you cannot take it. Okay. Therefore, but the idea is you will see, however, the data is, it is like an exponential form. It is increasing exponentially. So you need a non-linear curve to fit it. But however, you will know, we'll consider this problem, that this problem of exponential fitting can be boiled down to least square regression. Okay. So therefore, we are learning least square regression and we are giving it so much importance. Because any non-linear fitting, any polynomial fitting, you can boil it down to the least square problem using some tricks. Okay. What are the tricks? For example, if your data set is behaving like e to the power x, right? What you do? Take the log. Take the log. So log y is equal to x, isn't it? Yes. So it is just like a straight line form. Log y, you think of it as a capital Y, and this one is capital X. So is it y equal to x kind of line? I mean, this is not simple. If you see a e to the power x plus b, this is the regression line, suppose. It is for a exponential data set which is varying exponentially. Then how we can boil it down to least square? Take log on both sides. So log y equal to what? Log a plus x plus log b. No. Did I do any mistake? No, we cannot do this here. Because log is not distributed over additions, right? Let us make it simple. Let us take a e to the power x. So log a plus x. Take this as capital Y. Take this as capital A plus A. So this is a linear equation. Linear. So see how I boiled it down to this. So therefore, any exponential data set or any nonlinear polynomial forms, you can always boil it down to least square regression type. And therefore, so much importance is being given to least square form. You got the idea. So this is just a small catch I told you. Anyway, so you understood how we are computing the cost function and the loss function, right? So here I have taken the loss function to be squared, but you might not get an idea why we will take it as a square. So therefore we will do summation of EI. We will do summation of EI first and then check, okay? Okay, so you have done this formula yesterday, like last class, through Sylvester criteria. Okay, fine. So can we do that again? Can we carry forward this formula? And before beginning, I want to show that there are many types of regression, okay, which we should be learning, but it demands a lot of time actually, and I think it is suitable for a full course, mainly focused towards regression, which I always wanted to do. But you can see here all are listed at one form. Okay, you can see the first one is linear regression, which we will be learning. The second one is stochastic regression. Okay, I mean, you can see a lot of stochasticity is there. Not only a single line is used, single regression line. There is decision tree regression. How you are going to use decision tree for regression purpose. Random forest, k nearest neighbor regression, neural network regression. So this is like a classification problem is going on. You might be seeing that in your ML classes. Okay, especially this problem I feel. Okay, you might take, I think there is a playground, TensorFlow playground. On that website, you can use to classify different data sets. If your data set is very nicely distributed, you can just put a line. That is known as a decision boundary, right? And you compute the decision boundary. But however, if the data set is a very spiral looking like, then the linear regression line won't work. Then you have to use it in some other way. So this is where your neural network regression comes to play. Okay, SVM and all those things you can play around. I think that will be done in your class. Playground, TensorFlow playground. Those who want can Google it now also. TensorFlow playground. Okay, and try to Google it, and you will see a lot of different figures through which you can make classifications. Okay, then there is XGBoost regression also, as support vector regression, polynomial regression. We will just look into this regression a bit also in our course. However, other regression we are not looking at. I hope these will be covered in your ML. Okay, fine. But these are very interesting. I mean, to understand the concept from this one, how you develop all other regressions is very interesting. So you understood this strategy, right? So the error formula here, okay, with W0 W1, okay. So W0 W1 is something interesting. Before I move on, I will tell. So this W0 is in machine learning jargon. This W0 is referred to as a bias, and this W1 is referred to as a weight. Okay. So fine. I mean, just to make you aware of this terminology so that it doesn't appear new in other subjects. So this is our expression, final expression. If all of you agree, we can go through this. Okay. Like we are taking the average. We are taking the average of all the errors. Fine. We are taking the average of all the errors. Right. So what we are doing? There are n data points. N data points. Therefore, you are seeing 1 by n. Therefore, you are seeing 1 by n. Then we are taking the square of the residuals. What is residual? Residual is the difference between the actual data set and the regression line. So if the first data set is, hey, let us take this regression line, and this is the point x1, y1, and this is the regression line w0 plus w1x, right? Then can we move it down? Okay, what is this point will be? This point will be x1. This is x1. Yes, comma, the y w0 plus w1 x1, isn't it? So what we want to do, we want to compute the difference between this. That is the residual. That is the residual with us, right? So what it should be, but we are not taking only the residual. We are taking the square of the residual. So the square of the residual is y1 minus w0 plus w1 x1, then the square. The difference and the square. I will tell you why we are taking the square and not just the sum. Agree? So that's what you exactly see here, isn't it? That's what you exactly see here, isn't it? Do you agree or not? Yes. So that's for one point. Similarly, you can have another point also. You can have another point here. That is x2, y2. Similarly, you can have another point here, x3, y3. So similarly, you have to take these distances and sum it over, right? So that is the residual. And what is our job? Our job is to make the regression line as much close as possible to these given data points. Don't you agree? Our job is to make the regression line as much close to the data points xi, yi as much possible. That means as much close to the data point means the as much distance is less, to make the least distance between them, to make the least residual. Okay, and that means to make E minimize, or to minimize E as much possible. Okay, so we have to minimize E. To obtain the minimum loss, we have to optimize E W0 W1. But you know already that E is a function of two variables, W0 and W1. So therefore, you can easily apply the Sylvester criteria, right? So therefore, what we said, to find the optimizing solution, what you have to do is just to set grad E equal to 0, right? Because it's a function of two variables. After setting grad E equal to 0, we will either get a minimization condition or a maximization condition. To put the minimization condition, what you have to do? Enforce this step 2. The double partial derivative with respect to the first variable should be greater than 0. And the Sylvester criterion here, the determinant. Okay. Determinant of the Hessian, grad 2e, right, is greater than 0. So now can we start performing dou E by dou W not equal to 0 now? We have not yet found what this gives us, what this gives us. We have not yet found. Can we find it now? Dou E by dou W naught. Can we start? So I hope all of you have written down in your notebooks. So dou E by dou W naught equal to 0 equal to, just carefully think for one variable. This is a trick. I mean, don't just try to compute everything by notebook first. Try to overlook the problem first. All are square terms, right? And all have W naught inside. So just apply the chain rule of differentiation. So what is the chain rule? I mean, you have to do 1 by n will be fixed. Then the 2 will come out. The 2 will come out because it's a square term. So that, and 2 is coming out from each of the term. So I can take it common. Okay. Then what will happen? These terms won't have a square now. Won't have a square now. Okay, fine. So we can write that, but you will again differentiate with respect to W naught. So it will be -1. Yes, because it is minus W naught. It is minus W naught. In every case, it is minus W naught. So actually, minus will also come out. -2 by n, right? And what you will get? Y1 minus W0 plus W1 x1. Is it correct? Or did I do any mistake? I think so, correct. Or wrong? Similarly, I can do the next term. Y2 minus W0 plus W1 x2. Similarly, so on. I will do yn minus W0 plus W1 xn. Any wrong? Because see, we are doing dou e by dou W0. And minus W0 is there in each of the terms. If you take dou by dou W0 of Y1, what will be 0? Yes? Do you agree? No, it's the chain rule. It's the chain rule. Okay. Okay, I will do for one set, then you will understand. Okay. Let us do for one set. So dou by dou W0 of Y1 minus W0 plus W1 x1 squared, right? So what you will take? Take this guy as some f of W0. Take this whole guy as f of W0. So you are computing dou by dou W0 of f of W0, isn't it? Yes. So what it should be? Actually, there is W1 also. What we should do? No, actually, where is the confusion? Okay. So I will expand it for you. Shall we expand it? Then only I think it will be clear. No, we'll see. So dou by dou W0 of Y1, this one. So what will happen? You apply this as x square, right? So it will be 2 times of this x. So 2 times of Y1 minus W0 plus W1 x1, right? But inside part also you have to differentiate with respect to W0. Can we, so dou by dou W0 of Y1 minus W0 plus W1 x1, right? Isn't it? So what you are getting? Dou by dou W0 of Y1 is 0. Minus dou by dou W0 of minus W0 is -1. Plus dou by dou W0 of W1 x1, 0 again. So what you got? This -1 is coming outside. So -2 W0 plus W1 x1. Okay. So you can see this is for a one term. The same thing will happen for all of these terms, n terms. So therefore it will come outside -2. Fine. Okay. So these things we have to think. I mean, we cannot do always the same notebook kind of things. We have to think in our mind. Okay. Okay. So now can you think what else to do? But it is set to 0, right? But it is set to 0. So -2 by n cannot be 0. So only the bracketing thing has to be 0. Agree? Yeah. Bracketing thing. So what can we do? Can we write it as a summation? So this thing -2 by n, can we write it as a summation? Summation I equals to 1 to n yi minus W naught plus W1 xi. Or if I write it very clearly, minus 2 by n, I don't have to write the bracket again and again. Yi minus W naught minus W1 xi. Yes, fine. Agree? Okay. So what shall we do next? Can we take the summation inside? Can we take the summation inside? What are you getting? If you take the summation inside, you are getting something like this. Summation of yi, okay, I equal to 1 to n, okay, fine, minus w naught. So minus summation I equal to 1 to n w naught, okay, and w1 is constant, so I took it outside. I is equal to 1 to n xi. Yes, do you agree? So this one what you will get? So it is same. Yi, I equal to 1 to n, and w naught you are adding it n times. So it is n w naught, right? So minus n times w naught minus w1 summation of xi, I equal to 1 to n. I hope it is okay. So what to do now? Now can we do something here? We have to simplify it. Can we do something? Does anything comes to your mind? What to do here? We are taking the sum of all y elements. We are taking the sum of all x elements. Can we replace that big summation with something? Some value. Does it remind you of some value? Hmm? Does it remind you of some value? Huh? Yes, mean. You should be more confident. Squared mean. Yes, mean. Yes, because summation of yi divided by n, I equal to 1 to n, is nothing but the mean of y bar. And summation of xi, I equal to 1 to n divided by n is nothing but x bar. Isn't it? This you already have. So therefore, instead of these guys, what can I write? Minus 2 by n. This is n y bar, right? Minus n w naught minus w1 n x bar. Is it correct? Correct. So can we simplify it further? Can we simplify it further? So n all cancelled out. Minus 2 of y bar plus 2 w naught, okay, and plus 2 w1 x bar. Is it correct? So 2 common you make, so it is w naught plus w1 x bar minus y bar. Is it okay? Do you agree? You agree? Okay. So this you keep in mind now that dou E by dou W naught, finally we boiled it down to 2 times W naught plus W1 x bar minus y bar. Agree? I'm keeping the whatever 1-2 pages we have done, I'm listing it down as a result here. Okay. Let us go to the next one. Can we now solve dou E by dou W1? Can you solve similarly and let me know? Dou E by dou W1 equal to 0 is nothing but the same thing. Almost the same thing. Can we solve it? Can you try to solve? I will pause for a while. So you will get minus 2 by n, okay, and the x1 is coming to the front, right? It is not correct, minus. Why minus won't come? Y1 minus W0 minus W1 x1. Okay, is it correct? Then similarly x2 times y2 minus W0. This is x2, right? Same you carry on plus xn yn minus w naught minus w1 xn. Is it correct? Yeah. So can we write it in a summation form? Can we squeeze it down? So you're summing it over I equal to 1 to n, and this is xi, and this is yi minus w naught minus w1 xi. I hope it is correct, right? Can we take the summation side inside? Can we take the summation sign inside and then solve it or simplify it? What you are getting? So you will get something like minus 2 by n summation, I mean bigger bracket, summation I equal to 1 to n xi yi, the product of xi and yi, minus w naught, you take it out. This is xi, right? Yes. Then minus w1, take it out. Summation of xi squared. Okay. Yes. So can we simplify it further? Can we simplify it further or we'll stop here? What can we do more? Can we do anything more? Summation xi can be what can we do more? I mean, this one is good. I mean, this one, I feel that this one is good. Minus 2 by n. Summation xi yi is there. I equal to 1 to n. Okay. And this is minus w naught n x bar. Fine. W1 summation of xi squared. Now there are two terms. What can we do? Can we do something for this term and this term? That is my question to you. Can we simplify it further? Try to think. Don't let the notations trick you. Okay. So as other told, it is minus 2 by n. But then you will not have this n anymore. Okay. I mean, it will be cancelled out. So you will have n times xy bar minus n times w naught x bar minus n times w1 x square bar. Yes. So what you will get? Can you write it? So can I write it as, can you check this? W naught x bar minus w1 x square bar minus xy bar. Hmm? It is coming. Is it correct? Is correct, no? Plus C you're telling? Correct. Everyone agree? Sure. Because see, we are not it should not be you are thinking about n square. No. So what we are doing is, it is summation of x square. You understand? Because you are taking the mean. No, 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 no. We are not taking n here. We are writing summation of xi. We are writing summation of xi as n into x bar. You take this n here. Is that not true? X bar is summation xi by n. So summation xi is nothing but n x bar. Something inside. That is the n here. You try again by yourself. Then only you. You got it. See, the idea is we are just replacing. I mean, it is easy to get confused, but what we are doing here is just we are replacing this guy. Yeah, just we are replacing this guy. Okay, with this guy. Nothing else. Okay, good. So what we have got so far? Can we go back here again and write here dou E by dou W1 now is nothing but 2 times W naught x bar plus W1 x squared bar minus xy whole bar, right? These are the two terms we have got, fine? And we will set both of them to 0. We will set both of them to 0. So can you tell by solving, so it's a simultaneous set of equations. Can you tell me what is the value from these two guys? Can you tell me the value of W naught equals to what? W1 equals to what? By solving, this is equal to 0, right? This is equal to 0. Can you tell me by solving these two simultaneous equations, what is the expressions for W0 and W1? Yeah. What should be the value? So these are two equations and these are used to find, okay, the equations 1 and 2, okay, are used to find the regression coefficients. Used to find the regression coefficients. And those equations are nothing but those equations are known as the normal equations. Okay. So equations 1 and 2 are known as the normal equations. I hope you might have heard this term before also, maybe in interpolation in your previous semester, if possible. Might have. Because in interpolation also, I feel that you might have heard about, this term, normal equations. So these two equations are the normal equations. So can you tell me the expressions for W0 and W1? So through this, can you agree that W0 is, yes. So W0 will be something like y bar minus x bar w1, agree, and w1 will be xy whole bar minus x bar y bar divided by x squared bar minus x bar whole square. Agree? Hmm? So can you see carefully what is going on here? It is very nice formula. Okay. I mean, what it told you that through minimization argument, we can actually find the regression coefficients. Okay. And the regression coefficients depend solely on the mean x bar y bar and the mean of x square. Okay. And mean of xy bar square, x bar y bar. Right? Okay. But this might not be a good form. This might not be a very convenient form. Given a data set, given some data set to you, this might not be a convenient form to evaluate the regression coefficients. So therefore, what we will do next is write these expressions in some other way. Write these expressions in some other way. That should be our target today. Okay. So fine. So none of the points, none of the data point xi, yi from I is equal to 1 to n lie on the regression line, but it describes qualitatively the trend. The regression line describes the trend qualitatively. Okay. How to quantify? I mean, how to quantify that this regression line is the best one or has best estimated the data set? How to quantify? We till now don't have a quantification into how we can say that this regression line fits the data set the best. So therefore, this will lead us to find a quantity that is known as R2, that is coefficient of determination. Okay, we will find that. Okay. Okay. So can we have a alternate form for this estimates W0 and W1? That is what we will look next. An alternate form. Okay. So an alternate form. An alternate form for W0 and W1 can be convenient. An alternative form can be convenient, and how to find it? We'll go through it. Okay. So can we go back to the formula for W1? So W1 is equal to W1 is equal to xy whole bar minus then x square bar minus, agree. Can we do some simplification to this so that we can obtain in a very good form? Can means you have to open it up again. Open the expressions again, and can you bring it in term of something else? Some other known quantities. Can you bring it in some known quantities? A data set, how much the data set has spread out from the mean squared, what it is known as? Squared. You understood my question? Given a data set, there is a mean, and you are taking some data set and you are calculating how much the distance between the data set is from the mean squared. Okay. Okay. So W1, we have this formula, no? Xy whole bar minus x bar y bar divided by x square bar minus x bar whole square, right? So my question is, can we make it even more nicer? Can we have a more nicer expression? This okay, but this might be very hard to implement. Rather than this, can we have something, some expression which is more nice and more comfortable to evaluate? Hmm? Yes. So can we write in terms of that? Can we expand this? Have you done that? No. No. So you start. So what should we do this? 1 by n summation xi yi. I equal to 1 to n, right? Minus 1 by n. What can we write? Summation x bar yi. I equal to 1 to n. I mean, I am not opening both of it. I am opening only one of them. X bar I am keeping as it is. Because if we open both of them, there will be two summation signs and might be too complicated to handle. Okay. Then divide it by 1 by n summation xi square I equal to 1 to n, agree, minus x bar square, agree. Yes. So what else can we do after this? What else can you do? Can you take the common? So what we can do? We can write it as 1 by n summation xi minus x bar yi. Okay. Divided by 1 by n summation. What else? Xi square minus 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 n x bar square. Same things only. So what else you are getting? So can we cancel these out? Now this guy you are looking on screen, xi minus x bar into yi is nothing but sxy. What is this sxy? It is the covariance. It is the covariance. Okay. Then can you tell me what is this one? Did I do any mistake or anything? Which is the mistake? I don't think any mistake is there yet. Xi minus x bar, this is yi, right? Then I can write this into this form also. Xi minus x bar whole square. Here I think it's a mistake. We are trying to derive in terms of the variance. So therefore, that will create some confusion if you write that we cannot have that in terms of variance. Can we have in terms of variance? That's what I'm thinking. Minus xi square minus x bar whole square plus x bar whole square, that is fine. Minus 2 x bar and yes, I think we are correct. Can you write like this? Can you write like this? Do you agree? Can we write this one? Okay, in terms of this one, carefully check. You can do it. Very nice way of writing this. Very nice way of writing this. It might not look correct, but when you do it, it will turn out to be correct. Can you write it and check that it is actually correct? Hmm? While you look, it will appear incorrect. But when you do in your notebook, it will be correct. Hmm. That's what I'm telling you. This denominator, this whole denominator, you can replace with this denominator. Check it. Then you will know where this n is missing and all. Right? So what we got from this? Can you tell me? So finally you agree that this value, okay, this we can write, this W1, we can write as summation of xi minus x bar yi divided by summation xi minus x bar whole square, right? Do you agree now? Right? Now what is this? What is the numerator? The numerator is nothing but the covariance of x and y. So this is represented by Sxy divided by xi minus x bar whole square is the variance in x. So that is Sxx. So this is covariance of x comma y divided by variance of x. Got it? So variance of x is nothing but it measures the spread of data from the mean, and covariance of x and y, we will write it as cov x comma y. Agree? Huh? So W1 coefficient, what is our regression line? Regression line was W0 plus W1x, right? So W1 coefficient is nothing but the slope of the regression line. W1 is the slope of the regression line, isn't it? Why? Because it is multiplied by x. Y equal to mx plus c. Anything multiplied by x is like a slope. So W1 is like a slope. So the slope of the regression line is nothing but the ratio of the covariance of x comma y divided by the variance of x. Now, without any problem, this statement you can easily obtain the least square regression formula. Previous formula, can you see how it is a bit difficult to understand and catch it? But this one is a bit easy. W1, the slope of the regression line is nothing but the ratio of covariance of x and y and the variance of x. Agree? Fine. Okay. So to be more clear, what we can do is let us look at the expression summation I equal to 1 to n xi minus x bar into yi. Okay. And that is equal to, can we work more on this to derive a better expression? So can we write this as, mm, you help me in this. What else can we write this form? What else can we write this as? I mean, we are writing the same thing in a proper way, in a better formulating way. That's all we are doing here. That's all we are doing here. So I am asking that, can we write this in some other way? I mean, sorry, this is not y bar. Can we write this in some other way? So I can take y bar outside and I can write xi minus x bar. Do you agree or not? I equal to 1 to n. Yes. So what else can I do here? Can I open this bracket also? So y bar summation of xi I equal to 1 to n minus y bar and summation of x bar. Yes. Hmm? Is okay. After that, what I can do? This is nothing but y bar and x bar. This is y bar and x bar. That is 0. Isn't it? Huh? That is 0, right? Yeah. Then what we can do? I mean, it was not obvious to you that summation of xi minus x bar multiplied by y bar will turn out to be 0. You can understand why it happened unless you work it out, right? Now, why I did that? Can you tell me? Now, let us look into Sxy. What is Sxy? Yes, summation of xi minus x bar into yi. Now, can I do something? Can I borrow this idea into here? That's what I'm asking. Before doing that, therefore, I did that step. Can you do something on that? Yes. So, if I minus a 0, will it be a problem? If I do a minus 0, will it be a problem? No. So, instead of 0, can I put this expression? Huh? Instead of 0, can I put that expression? There won't be any difference because it is 0. Right? Agree. Everyone say yes or no. Huh? Yes or no? Why? Huh? Summation of something is 0 and I am minusing it with 0 and I am putting that expression. Why there is a problem? Okay. So suppose xi minus x bar into yi, and instead of 0, I will write that summation I equal to 1 to n xi minus x bar into y bar. Hmm? No, that is 0. No, that summation y bar is 0. Hmm? And I can write this further as xi minus x bar into yi minus y bar. Yes. So what else can we do? So can you now see that instead of just writing Sxy like this, there is an alternative form like this. There is an alternative form. So now you can better understand why I am calling this Sxy as the covariance. X from the mean multiplied how much distance y from the mean. Okay. But this is a useful form. So what we understood? So far, can we write whatever we understood so far? So y cap is equal to w naught plus w1x. This is the regression line. Okay. And what is the regression coefficient or the slope w1? It is nothing but the covariance of x and y divided by the variance of x. And what is the covariance of x and y? It is nothing but summation I equal to 1 to n xi minus x bar into yi minus y bar divided by this is xi minus x bar whole square. I equal to 1 to n. Agree. This is W1, right? Now can I find W naught? W naught is equal to y bar minus x bar W1. Finish. So this is all about regression. To obtain this formula, since morning we were deriving all these things. I mean, so that you will know the process, how it comes. I mean, not just we'll write this formula and give the data and you will do it. Okay. At least now you understand why we wrote it in terms of covariance of x comma y divided by the variance of x. Right. But why you believe that this w naught w1 is the minimum? We wanted, what was our aim? Our aim was to find w naught and w1 such that the cost function is minimum. That is E w naught w1 is minimum. But why do you believe me that this w naught w1 actually gives the minimum? You have to check the inequalities. The determinant of the Hessian should be greater than 0 and the double derivative with respect to first variable should be greater than 0. Did we check that? No. So let's check that. Let's check that. So what should be the case? Can you tell me? So dou 2E by dou W naught 2 is equal to what? Dou 2E by dou W naught 2. Huh? 0. We already found it out, no? Just take another W naught derivative. Check that, you will find it to be 2, and that is greater than 0. You will find it to be 2, that is greater than 0. Yes, you are getting right. Good. And we can take now the mixed derivative. Try the mixed derivative. Try the mixed derivative also. You do that in your home, and I will check it next class. The mixed derivative, you understand. Determinant of the Hessian. Check that. That also determinant of the Hessian. That also will become greater than 0. Okay. So therefore, those W0 and W1 as above give us the minimized cost function EW0 W1. Therefore, this is the regression line with, that is, y cap is equal to W0 plus W1x with W0 this and W1 this, which gives us the best fit or the best estimate for the given set of data. Okay. So you can think of this. One more idea is you can think of this regression as a neural network also. What is a neural network? I hope you have already seen that in your ML classes in the beginning. Okay. What it is, like, you can see that it has weights W0 and W1. This is another visualization about regression. Okay. And here you give 1. Here you give X. Okay. So inputs. Okay. W0, W1 are like the weights, right? And then what you do, you take the sum, that is W0 plus W1x, right? And that is your output y cap. That's the output. That is equal to W0 plus W1x. Okay. Okay. Now let us go back to the class and think why we did the EW0 W1 as summation EI squared. Why? Why this and not summation of EI? Yeah, we said this question in the beginning, right? Why we took the square? Why not the sum? Can we take the sum and check what we get? Uh-huh. Huh? Cancel out. So it should be? No, no, no. It will cancel out, you are telling, right? It will cancel out and give us? Huh? Sure. Not exactly 0. Yes. I mean, no, what do you think? Like, we are not taking EI, you are correct. You are correct. I mean, we are not taking EI because some are in positive. If point is below, it will be negative. So positive, negative, cancel out. But you are telling cancelling out. But cancelling out final term, which one you will get? Whether positive or negative or what? Can be either. Can be either. Okay, let's see. Huh? Okay. So let us take, okay, let us take summation of EX. That is I equal to 1 to n. So summation of EI is nothing but summation of what I can write. Summation of, yeah, tell me the expression. Yi minus dou, huh? Yi minus y cap, right? Huh. So can we expand these things further? Y minus W naught plus minus W1x, right? What are W naught, W1? Can we substitute? W naught we already did, no? W naught is maybe we can write in a different way. We don't have to write the complicated expressions. Don't turn to complicated expressions. Can you simplify it with this? That's what I'm asking. Write yi minus W naught minus W1 xi. Sorry, it should be xi, right? It should not be x, no. It should be xi, right? Xi, yes. Can you do something with this? Can you do something with this? Can I write this as, yeah, summation? Can I write this as yi minus y bar minus x bar w1 minus w1 xi? I am just expanding w naught. Yes, agree. I am just expanding what is w naught written previously, right? Okay. Now, can you gather the terms? Can you gather the terms? So summation yi minus y bar minus xi. Tell me, did I do any mistake here? W1. Is this correct? Should be plus x bar. Ah. Is it plus x bar? No. Huh?
Plus x bar. Minus of xi plus x bar.
Okay. Right. What you are getting? Write something. Can I expand W naught? What is W naught? Y bar minus x bar W1. Agree? So what happened? So that should be summation of yi minus y bar minus xi minus x bar W1. Now do you agree? Yes. So if I take the summation, what should happen? What should happen? So summation of yi minus y bar, fine, minus w1 of summation xi minus x bar. Agree. What is this quantity? What is this quantity? Can you tell me what is this quantity? Think carefully. Think very carefully. What is this quantity? Hmm? Yes. Shall I explain? Summation of yi minus summation of this is ny bar minus w1 This is summation x by, this is nx bar. Okay, summation yi can I write ny bar minus ny bar minus w1 nx bar minus nx bar. What is this? 0 minus 0, 0. So this is a perfect example that some things which are visible to you suddenly doesn't come to your mind. Okay, but they are there. They are there, isn't it? So therefore, this zero quantity, people were telling covariance, variance, so many things. But just to have a visualization, if I took inside the summation, what happens? Right? This doesn't turn out to be like, doesn't look to be zero. But when you go inside, it looks zero. So what do you got from this? Okay, let us come back. You got from this that when you take the residuals and sum of all residuals for data sets xi, yi, I equal to 1 to n, it will always turn out to be 0. It will always turn out to be 0, right? So therefore, so the statement that it sometimes can be 0, sometimes cannot be 0, can be 0 is wrong. It will always be 0. It will always be 0. Okay. The sum of residuals will always be 0. Therefore, it's not a good choice for the error. It's not a good choice for the cost function. Right? Therefore, this is why you are taking summation of ei squared. So therefore, this is not a good choice. Not a good choice for optimization. So this is not a good choice for optimization. Do you agree? Yes. Therefore, we are taking summation of ei squared. Okay. So therefore, it's not a good estimate. Okay. It's not a good estimate for optimization to compare the best fit. Therefore, we are taking summation of ei squared, right? Okay. Now, let us look into another concept, that is R2, coefficient of determination. Coefficient of determination. Okay. What is this R2? Okay. So let us look at the square. So what I want you to look at is something here. That is, let us start with yi minus y bar. So we are starting with some expressions only to reach to a particular choice of a candidate. Okay. Or particular choice of R2. Okay. So you might not get an idea why we start from this, because it's like a reverse engineering. Because in order to find this R2 value, previously we have to do some simplifications. Those simplifications we can directly use it. So what I suggest you is, whenever I write something, look at the flow and then try to understand why we took it like that. Then you can appreciate better why we have made that decision. Okay, you got the idea. So can we look into yi minus y bar? Yi minus y bar means how the points yi are far away from the mean y bar. Okay, that's what we are computing here. So how can I simplify this? I can simplify this by something, by adding and subtracting yi cap. So I am adding yi cap, okay? And is this correct? I am subtracting yi cap. Is this correct? Yes, it's correct, because I am subtracting and adding yi cap, and yi minus y bar is as intact. It's correct. Okay. What can I do with this? So if I take yi minus y bar whole square, okay, if I take yi minus y bar whole square, then what will I get? What will I get? Yes. So mind you, this equation is going to give you a very nice and important condition, really very important condition. So I suggest everyone to try this. If you take the square, what you will get? So a plus b whole square. So yi cap minus y bar whole square plus yi minus yi cap whole square minus, sorry, 2 plus 2ab yi cap minus y bar into yi minus yi cap. Do you agree to this? I am taking this square, nothing else. A plus b whole square. A square plus b square plus 2ab. Okay. Now, can we look into cross term? Can we look into the cross term, that is yi cap minus y bar into yi minus yi cap? Can you simplify this? Can you simplify this further? Is my question to you. With whatever information we have already. With whatever information we have already. I mean to say that write this in terms of the covariance and variance. Write this expression in terms of covariance and variance. See, only then you will see very nicely, suddenly a very good relation is popping up. Very good relation will pop up. Can you tell me? So can you come to a conclusion that summation of, okay, yi cap minus y bar into yi minus yi cap, okay, is equal to sxy minus sxx, okay, w1 times w. Can you come to this conclusion? Try this. I'll give you 5 minutes. Okay. So let us come back to this equation. Okay. Let us come back to this equation written here. Let me check, is that the correct equation in my notebook? So yi minus y bar whole square we are taking. Yes, yes. Okay, good. Let us come back to this equation. Okay. Let us come back to this equation here and apply summation on both sides. Apply summation on both sides to this equation. And when you do that, you will get something like summation yi minus y bar whole square, okay, I equal to 1 to n, equal to summation I equal to 1 to n yi cap minus y bar whole square plus summation yi minus yi cap whole square plus 0. Okay, plus 0, because summation of this cross term is 0. That was the whole motivation to do this step. That was the whole motivation to do that step. You got that idea? I wanted to show you that the cross term, when you sum it up, it will boil down to 0. So therefore it is 0. Okay. Now this simple looking thing is something very interesting and very important. This thing you are seeing over here, do you think it is something special? Do you think it is something special? Yes, it is known as SST. Okay, what is SST? I will tell you. Okay, will come. Then what is the second term? Yi cap minus y bar whole square. This is nothing but SSR. Okay. Okay. Then let us go back to the next term over here. This term over here, which you are seeing, is nothing but SSRS. Okay. What is SST? SST is nothing but sum of square. Sum of squares. This is the total. Okay. What is SS capital R? Okay. SS capital R is sum of squares, but for regressions. Okay. What is SSRS? SSRS is nothing but sum of squares. Residual. So what we got, sum of squares, total sum of squares is nothing but sum of squares related to regression plus sum of squares related to the residuals. Okay. You can see yi minus yi cap is a residual. Right? You can see that, no? Residual square. Yes. It is sum of square residual. Yes. Why it is residual? Why it is residual? Yeah. Okay. So now you know the relation that sum of squares total is equal to sum of squares regression plus sum of square residual. Okay. Now what can we do with this? Okay. What can we do with this? So the coefficient of determination, that is R2, is defined as, okay, is defined as SSR divided by SST. This is known as the coefficient of determination. This is known as the coefficient of determination, that is R2, that is equal to SSR divided by SST. Okay. So this is also equal to, can you tell me, 1 minus SS residual divided by SST. Okay. So what does it tell you? It tells you that, try to understand that, it tells you that R2 can lie in between 0 and 1. It is 1 minus something. It is 1 minus something, and that something is also less than 1. But why it is less than 1? I suggest you guys have a thought. Okay. To be honest, SS res divided by SS total. SS total is the sum of that. So SS total is always the big guy. So therefore you are dividing the big guy. Therefore it will be always less than 1. So therefore 1 minus something less than 1 is should always lie in between 0 and 1. Right? So this helps to understand why the coefficient of determination should be in between 0 and 1. Okay. Now, okay. Now can we what do you call that? Open the term. Can we open the term of R2 equal to SSR by SST? SSR by SST. Can we write this expression? Can we write like this? Yes, we can write like this because yi minus yi cap whole square. Okay. So SYY, it is just like a variance. Okay. And SXY, SSR is nothing but SXY times W1. That I suggest you try to look. There are some expressions where you need to think from your side. I mean, you need some write up to understand. Okay. So what can we do further? Can we write W1? What is W1? W1 is SXY divided by SXX. Can we write that? So it is nothing but XXY squared divided by SXX SYY. Okay. Now, can we write like that? 0 less than equal to SXY whole squared divided by SXX SYY less than 1. Okay. Now, what does it imply? It implies that your SXY, okay, is in between -1 and 1 because we are taking a square root. If you squared it, it can be lying in the negative, and if you square it can come to the positive side. So this guy lies in between -1 and 1, and this guy is nothing but the R. Okay, this is nothing but R, and this R is known as the correlation coefficient. So you understand why, what is R2 and what is R. R2 is nothing but coefficient of determination, but R, the same thing which you might have learned in probability course and statistics, has turned out very nicely to be the correlation coefficient. Correlation coefficient, I am sure you remember this term. I am sure you remember this term. You see how nicely this term popped up. Yes, I suggest please try to look into this very carefully when you go. So what is R2? R2 can lie in between 0 and 1, whereas the correlation coefficient can lie in between -1 and 1. Okay. So you agree, right? So now you know how correlation coefficient comes, how we derived correlation coefficient just with the data set xi, ya, and how we derived coefficient of determination R2, and R2 lies in between 0 and 1, whereas R, that is the correlation coefficient, lies in between -1 and 1. And why we call it a correlation coefficient? Because you already have seen this in your probability class. Sxy divided by root over of Sxx root over Syy. Okay. I mean, you can look into some statistics probability books why it is known as correlation coefficient. I think you already know, most of you. Okay. I mean, if they are correlated, it is +1. If they are fully non-correlated, -1. Okay. I mean, negatively correlated, it is -1. Totally, I mean, if they are progressing towards 1, that means they are having a positive correlation. Okay. Agree? Okay. So try to understand these things. The idea through this process is to make the connection in between various roots. Okay. Suddenly you saw how to obtain correlation, how to obtain regression coefficients. How regression coefficients are related to variance and covariance. Okay. What is R2? R2 is coefficient of determination. Now using R2, how we can find correlation coefficient? You see, through one process, how we branched out to multiple things. This is the beauty of it. This is the beauty of it. Okay. Now, why we need to find this R2? Why we need to find this R2? Because this R2 provides a quantitative measure for us to tell whether the regression line is a good fit or not. That time I told you, how can we know there is no quantitative measure that a regression line can be a good fit? We found the minimization condition and obtained W0, W1. But is there a quantitative relation which can tell that, okay, it is this much percent, this much percent and it is better fit? So therefore, if, let me write, these are the thoughts, okay? If, okay, if R2 is close to 1, then it means that regression line runs close to the data points. Point 2, if R2 is closing to 0, then regression line fails to capture the actual data points. Okay. Third, if R is greater than 0, it is known as a if R is greater than 0, it is known as positive. Yes, positive correlation. That means if y increases as x increases. If x is increasing, y will also increase. Okay. Fourth point, if R is less than 0, it is known as, yes, negative correlation. That means as x is increasing, y will decrease. Y will decrease as x is increasing. Okay. Now, fifth point is if R is closer to 0, that means there is no correlation at all. There is no correlation between x and y. And that means y and x are not dependent on each other. Yes, isn't it? I mean, it doesn't depend how y and x are going through. Y is not depending on x. They don't have any correlation. Yes. There is sixth and most important point is high values of R2 is necessarily good, but might indicate overfitting also. Okay. High values of R2 might be good, but might indicate overfitting also. So you should not always believe that high values of R2 is always good. if R2 is 0.99 or R2 is exactly 1, then you have to check for overfitting, if overfitting is happening or not. I mean, it is not always good that high values are always good. It might be a sign of overfitting. Now I want to ask you a very important question, which you might get in various interviews also. I mean, if you are attending any interview for data science and all, they can, if they are asking you a question on regression, they might ask, I mean, another question which I want to ask to the whole class. Okay. Will regression line, I mean, you are considering least square regression, will regression line pass through the means of X and Y? Will regression line pass through the means of X and Y? I mean to say, will X bar, Y bar lie on the regression line? Will X bar, Y bar lie on the regression line? Is it mandatory? Or might not lie? What do you think? Hmm? What do you think? I am can you think what I mean by this line? What I am asking is, you have set of data points, no? You have a set of data points, right? And it is the set of data points, no? What you do is do a least square regression. If you do a least square regression, you are getting a line like this, right? Now what I am asking is whether the mean, I mean there can be a mean here, X bar, Y bar, will it pass through the regression line? Or it might or might not be? Might be, might not. Might, what does it mean might be? That means it also might not be. If you want to say must be, it should pass. It must pass through regression line. Always. Is this correct? X bar, Y bar will always pass through the regression line. Will always pass. Why? Huh? Huh. So technically what we are asking is whether X bar, Y bar point satisfy the regression line. Isn't it? Isn't it? So our regression line is W0 plus W1X. So does it satisfy Y bar equal to W0 plus W1X bar? That is a so simple question. So the answer is yes. Whatever you do, whichever problem you consider in least square regression, always the mean X bar and Y bar will always lie on the regression line. Always lie on the best fit line. Okay. So this is one of the very nice observations we have with us. Yes. Anything else? Hmm? So what we have learned so far, can we summarize? What have we learned so far? I mean, we have learned so far that least square regression. Okay, we learned linear regression, that if data are spread in a linear fashion, you can estimate them by y cap is equal to W0 plus W1X, where W1 is equal to Sxy divided by Sxx. Sxy is the covariance between X and Y, and Sxx is the variance of X. Okay. So you can write it as covariance of xy divided by variance of x, right? And W naught was y bar minus x bar W1. Yes. So y bar and x bar are the mean of x and y dataset, and W1 you already have previously. Okay, good. What is Sxx? Sxx is nothing but summation of xi minus x bar whole square I equal to 1 to n. And Sxy is nothing but summation of xi minus x bar into yi minus y bar I equal to 1 to n. Do you agree? Okay. Then we understood one important term, that is SST, that is sum of squares total, is nothing but sum of squares. Yes, SS residual. Okay. Sum of square regression plus sum of square residuals. Okay. So that is nothing but summation of yi minus y bar whole square is equal to summation of yi cap minus y bar whole square plus summation of yi minus yi hat whole square. Yes, good. Then third is we learned the coefficient of determination, that is R2 is nothing but SSR divided by SST, and R2 will lie in between 0 and 1. Okay, so this is known as the coefficient of determination. Okay, and if you take the square root of it, this becomes R, that is the correlation coefficient, and it lies in between -1 and 1. So correlation coefficient. Okay, if we always, for a good fit, R needs to increase. Okay, R needs to increase, but high R might indicate overfitting. High values of R might indicate overfitting. Okay, and correlation coefficient you already know. If it is -1, it is negatively correlated. If it is +1, it is positively correlated. If it is 0, they are not dependent. There are no correlation is there between x and y. Okay, fine. So what is coming ahead? Okay, maybe we can cover it in tomorrow's class. What is coming ahead? Coming ahead, we will learn about many things. That is, what is Murray-Penrose generalized inverse. Okay, I hope many people who are doing reservoir computing, many people who are doing projects on reservoir computing, they must have come through this inverse, Murray-Penrose generalized inverse. Actually, it is so important that Python has a predefined function for that. And what is that function? That function is PINV, that is pseudo inverse. P for pseudo, INV for inverse, P inverse. Okay, we will learn why this P inverse is useful. Okay, and you will see that pseudo inverse is useful where, if you have, for example, we will consider tomorrow one problem after the test, that is, for example, consider person X. Okay, so the person X spends some time on Facebook, some time on Insta, sometime on X, sometimes on Y. Okay, apps. Okay, and when they spend a lot of times on apps, the brain rot. Okay, brain rot happens. So we want to find an equation for how much brain rot is happening when they use different apps. Okay, we will do this problem tomorrow. Okay, so when Y regression line depends on not only, now today it depends only one X. Yes, y equal to W0 plus W1x. But when it depends on x1, two different coefficients, x1 and x2, how Murray-Penrose generalized inverse is going to help you? Tomorrow we will learn this concept. Okay, so there will be some linear algebra. Okay, some linear algebra. And through linear algebraic concept, we will learn how to derive that regression. Okay, and then we will solve a problem. Same problem, like if y depends on x1, x2, then how can we do a regression line based on that? Do you agree? You agree? Then second thing, we will learn how to perform regression, for nonlinear functions. if you have nonlinear functions like today's class, I told you, if you have something like an exponential increasing data set, then linear regression won't help you, right? Then how you perform regression for nonlinear functions? Okay. Then third, we will see various Python codes. Okay, we will see various Python codes and various examples and commands also. So you don't have to type much. You just use the commands and it will do least square regression for you. It will do data sets, give data sets, whether it follows the exponential data set, whatever, but optimize fit command. It will automatically do regression line for you. And we will see polynomial regression also. If your data sets are like this, if your data set are like sine kind of things oscillating, then what kind of polynomial can fit that? We don't know. If you take your lifestyle, for example, when you have breakfast and when you have other things, it will follow a periodic pattern, no? Because at every particular time you are having something in a day. You are doing everything similar in every day almost, right? So it will always be a periodic way, right? If it is a periodic data set, what kind of regression line can fit that? So you should approximate this by different polynomial forms. You will see that as you increase the order of polynomial, the fit happens more and more good. Okay, that we'll see with Python tomorrow. Yeah. So this is what is remaining for regression. This is what is remaining for regression. So I think we can complete that in tomorrow's class. Okay. Fine. Stop.